Hello, my name is Hayden Morgan, and I'll be presenting on LQG visual servoing of a quadrotor system. The objective of this presentation is to dive into the derivation and implementation of a linear quadratic Gaussian, or LQG controller, on a quadrotor system, and particularly for the case of visual servoing. We're going to demonstrate that in simulation. The motivation will begin with a definition. Visual servoing is simply the controlling of a system, in our case a quadrotor, using pixel error instead of some other state's error. Visual servoing enables a variety of applications, including general visual alignment, vision-based landing in GPS-denied areas, payload acquisition, localization, a variety of applications in addition to those. We'll begin with our quadrotor description. We'll define our velocity states in the body frame as u, v, and w. Our phi, theta, and psi terms define our Euler angle rotation states of our aircraft. P, Q, and R are rotational rates. Our inputs to the system are going to be defined generally as the net thrust caused upward by all the propellers, and tau x, y, and z are just the moments in the x, y, and z components of the body frame received from differential thrusts in these different propellers. So the quadrotor dynamics that we're going to look over, all credit goes to Francesco Sabatino. They're very complicated in his work, quadrotor control modeling, nonlinear control design and simulation, at his thesis for KTH Royal Institute of Technology in Sweden. The very, very hairy translational and rotational equations of motion. We won't dive into where they came from. Just note that these are what they are, and that Sabatino is the one who derived them. Quadrotor state-space model is really what we're interested in. So we're going to take those equations of motion, we're going to linearize them into this form that is common for linear systems, where we have x tilde dot equals ax tilde plus bu tilde, and our output y is equal to cx tilde plus bu tilde, where x tilde is the difference between our state and our equilibrium point that we've defined, that we linearized the system about, and u tilde is our inputs minus the equilibrium input required to obtain that state. So for our case, we defined an equilibrium point at just stable level flight, no velocity, no angles, defining our rotation or our orientation, no angular rates. To do that, we just had to overcome gravity with our thrust, no torques on our system. And we get these really sparse, simple matrices, which is really convenient and nice. We're going to assume for our case that we're going to observe our states directly. So our C matrix is just a 9x9 identity matrix, meaning that our final system is as before, except this y term is now just equal to our observed states of our system directly. Normally, you would have accelerometers, other sensors that you'd be observing to get those states, but for simplicity, we're going to make that assumption. Another simplifying assumption we're going to make is that our desired states are constant, and in our case, we're going to be commanding the velocity states of our aircraft. By assuming they're constant, we can define these error terms, which is the difference between the desired state and our current state. And then the derivative of these error terms is actually the same as the derivative of these states, since these are all constants. So we're going to make that substitution, make that assumption, and we'll talk about the consequences later. LQG control is simply just a combination of LQR control complemented by a Kalman filter. The Kalman filter takes the outputs of your system, it estimates the states of your system through noise and other disturbances, and then it passes it into your LQR controller for reference to compare against the desired states to get your input. So we're going to dive into each of these components separately. LQR control seeks to minimize this infinite horizon quadratic cost function, where we have these quadratic terms on our states with weighting matrices, weighting matrix Q, and our inputs with weighting matrix R. These Q and R matrices can be selected to put more emphasis on getting somewhere quicker, or regulating our states faster, or putting less input into our system. And the solution to this is actually just a regular feedback term where K, this matrix, is defined using the R from this weighting matrix, the B from our state space equations, and P being the algebraic Riccati equation solution to this. We won't dive into that for simplicity. There's a lot of literature on that. Weight selection, by assuming diagonal matrices, we can use Bryson's rule, which says that if we make these diagonal terms in Q 1 over the square root of some desired maximum value as just a heuristic, then it helps us to be able to kind of normalize all of these terms so that they appropriately influence the optimal solution of our model. So we'll be using this for our tuning cases. Kalman filter observer uses a similar model, except it adds zero mean Gaussian noise onto the propagation equations of our system and our noise in our sensors or in our observed outputs. And Qn and Rn are just going to be the covariance matrices that describe that Gaussian noise characteristic for W and V respectively. This is really, a Kalman filter is just an optimal Leuenberger observer, where we've defined our Leuenberger observer as follows, and X hat is our observed or estimated state, and it's updated using this difference between what our estimated state should be having as outputs versus what we're actually seeing as outputs from our sensors, multiplied by this innovation weight or term. And this L matrix, or the Kalman gain as we call it, is obtained optimally by seeking to minimize the expectation between the squared error, where the error is just the difference between our states and our estimated states. And like the LQR controller, the Kalman filter gains can be obtained using this form through the Kalman-Busse filter derivation, where P is just the solution to this algebraic Riccati equation. So on to visual servoing. For visual servoing, we're going to start out with the assumption that we have a regular image that we're observing with U and V pixel coordinates in this discrete space that we'll define with epsilon, where some feature epsilon I is described by a point in here with coordinates UI and VI. Visual servoing makes the assumption that you use a pinhole camera model typically, and the idea is that an object in your camera or in your image is going to be just a projection of that object onto a plane that is the distance of the focal length away from your camera center. And this is a continuous space, as you can see, whereas before it was a discrete space. And so we can convert our discrete pixel coordinates into this continuous space that we use for visual servoing by simply just translating from the top corner to half of the image in each direction, subtracting that off, and then dividing by the pixels per meter to put that into a meter format instead of a pixel format. And then we get these xi and yi coordinates for a given feature. An interaction matrix is really the meat of visual servoing. And it's defined as follows. It uses the xy coordinates from our features as before, but it also involves the depth of that feature in the world, in the camera frame. We'll talk about how to get that, and then the focal length of the camera right here. This interaction matrix is just a Jacobian that defines the interaction between a camera's velocity and angular velocity to the pixel or the feature's velocity that we're observing. So if we stack three features on top of each other, if we observe three features, then we can actually define this square Jacobian matrix, and we can invert it to actually solve for the velocity terms of the camera that we need to produce these pixel motions. And so we'll define P dot C as these pixel motions that we're trying to describe. And we're going to use this by defining our desired pixel states that we want our targets to be at. We're going to put them into that Cartesian frame, the continuous space, and then we're going to define the difference between where the pixels actually, or where the feature actually is versus where it should be on that frame. And we'll use that in the feedback term to define this error or the rates of our pixels that we want for our system. So we can plug in that feedback term or those feedback dynamics into our equation, and we can actually just pick off the velocity components of our system to get the camera velocity as follows with this equation. For our sake, we assume that we had an RGBD camera, that we could obtain depth for each of these feature points directly. And we ignore the rotational terms because the quadrotor has dynamics of its own that it needs to take advantage of. And so we're just going to focus on getting the quadrotor to follow these velocity components. We'll talk about the consequences of that later. We'll rotate those velocity components from the camera to the body frame to get our desired body frame velocities for our states. In simulation, developed a quadrotor camera system in Python. Here's my GitHub account for the repo. We defined 3-point targets in the environment, some system parameters, HD camera with focal length of a centimeter, Kalman filter parameters, LQR parameters, some visual servoing parameters. We put the desired pixels in the top right corner and used 1/5 as our as our gain on our visual servoing feedback. So in quick demonstration, here's how it performed. I'm going to double the speed. It's relatively slow, honestly. But you can see that we start out with projections onto our image as follows, down in this corner. And they kind of veer around and sweep, and then converge eventually onto these 3 points, just as desired. So it works fairly well. A little slow, but it works. Okay. So here's a still image of the final result. It was able to converge. The states are able to converge. You notice we didn't command any positions, but because of the way that visual servoing worked, it actually converged to a set position, as you would expect. I had a little bit of a delay behind the commanded velocities in X, Y, and Z, and the actual velocities. I'll talk about why that is in just a second. But it seemed to work very well. Some notes on tuning. Aggressive tuning led to significant overshoot and instability sometimes. The linearized model assumed it was stable level flight. That's to be expected. If it pitched too much, then suddenly it was trying to assume that it was stable or level and moving when it wasn't. When we ignored the rotational commands to accommodate the dynamics, that led to the sweeping action that we saw of the pixels kind of veering out to the side and then coming back in. If we were able to directly control the rotation at the same time with the quadrotor, then we wouldn't see that. It would just directly linearly translate into the desired locations. But quadrotor dynamics would be influenced if we had commanded those as well. Velocity controller behaved like a standard proportional controller, slowed down as it got there. Could have been improved if we put saturation on it potentially. And then you notice that tracking delay, that's really just due to the idea that we made the assumption that the desired velocity was constant for the commands. And because of that, it was always trying to catch up to a constant desired velocity, and it never was able to. Conclusions: quadrotor controller was able to, or the LQG controller was able to control the quadrotor to a desired velocity, which was really nice for visual servoing. The tuning was much more intuitive than trying to think about pole placement in a PID setting through LQR component of the LQG controller. And the linearization really isn't meant to be aggressive. It's not meant to do acrobatic maneuvers, and it works decently for very slow convergent applications, but I wouldn't use it for much beyond that.